So we have dealt with collimation. Now I want to deal with the second effect that we have to deal with, and that is the attenuation of the emitted X-rays. We have mentioned that this is one of the things that we'd ideally not have. And now what we are going to look at is an image of an object that is homogeneous. We'll take it, say it's a sphere. It's filled with a liquid that is doped with, say, technetium-99. If it is a liquid, it has a constant radioactivity. It has constant specific activity in the tissue. Yet, if we put that sphere into the scanner, this is the image we get. We are getting bright intensity at the surface, and it is dark inside. This is not the tissue radioactivity, CT, that we would like to measure. We know in this case it is constant, it is homogeneous, yet what we're measuring is something that's bright on the outside and dark on the inside. So what is the cause for this intensity distortion? And I want to now explain this. So we'll take here a situation, an abstract situation. We have a bath filled with water and some radioactive substance. We'll look at this point here, and we'll assume that this water has a solution of metastable technetium-99. So it's an aqueous solution that's in this water bath. Now we have the linear attenuation coefficient of water at 140 kiloelectron volts. That's the energy of the photons of this tracer here of metastable technetium-99. This linear attenuation coefficient is 0.16 per centimeter. Here's our detector. So we have here the collimator and the camera behind it. We'll come to the other elements of the camera shortly. We introduce here the distance, and we'll say this object. We'll look here now at the pointwise, at one point here that is about 5 centimeters away from the camera. So we know the linear attenuation coefficient, we have a homogeneous object, and now we can calculate the attenuation. So this is something that a linear attenuation coefficient expressed in per centimeter, 0.16 per centimeter, is not very intuitive, and so it makes much more sense to understand the numbers that we're going to provide by looking at the half value layer. So we have seen that the half value layer is 0.7 divided by mu, and in this case the half value layer is 4.5 centimeters for technetium in water. So if we're 5 centimeters away, we should essentially have a reduction of the signal that is a bit more than half of the signal. And so we'll talk here about the attenuation T as a function of the distance d. So the distance is how far our object is away from the scanner. Now we've seen from X-rays that the intensity as a function of distance d is given by the original intensity, the incident X-ray. That's the number of X-rays that are emitted in this direction, n0 times e to the minus mu d. So with this we can calculate the attenuation. And the attenuation is given by the number of photons detected divided by the number of photons emitted in that direction, and that's e to the minus mu d. So in this case, the attenuation is 0.46. So we are detecting only 46% of the photons that are emitted in that direction at a distance of 5 centimeters. Now one consequence is, if this is clearly distance dependent, the deeper we are, the more attenuation we have. And so the attenuation, the reduction of the X-rays that are being detected, depends on the object dimensions as well as on where the source is. So the distance here, d, where our source is, this part here, is source location, and it depends on the size of our object. And here's 3 examples of an object with 10 centimeters length, 20 centimeters length, and 30 centimeters length. And we look at the activity detected here at the center of the object. It is decreasing with increasing object size, because the further away we are at the center from the surface, the longer is the distance the X-ray has to travel through the object, and so the less likely we are to detect an X-ray. So let's take the next situation here. We're 10 centimeters away. in this case. So the distance is 10 centimeters. So we roughly have 2 times the distance, so it's the square of the attenuation, so 0.46 squared, that is roughly 0.21. So we have 21% of the photons that will survive a travel of 10 centimeters through water. And the last example here is 15 centimeters of a distance, and here we're ending up only detecting only 10% of the photons. So we have 5 centimeters, 10 centimeters, and here we have 15 centimeters from the center to the outside. And this is exactly what is happening here. The substance that's at the surface of the sphere does not travel much to get to the detector, does not travel much through our water solution, so it is hardly attenuated. Whereas for the image generation, the substance that's at the center of the sphere will always have to travel the radius of the sphere, so it's consistently being much more attenuated, and that's why you are seeing an image that instead of being homogeneous is bright on the edge and dark on the inside. To conclude, if we're looking here at the point source, we have taken here a homogeneous path. We've looked at 3 different distances to the camera. We're seeing quite clearly that the attenuation depends on the location of the source in the tissue relative to the camera. There's a second consequence here, and that this attenuation depends on the specific radioactive substance that we're using, on the specific gamma emitter. We have here the situation of, in the solid line, of metastable technetium-99. We have the dashed line is iodine-131, and the small dashed line here is thallium-201. And you can see that there is a difference in attenuation based on the type of isotope. So that is because the linear attenuation coefficient is not uniform for any substance with photon energy. It depends on the photon energy, and so this absorption depends on the tracer that we're using. Of course, here would be the activity that we detect if we had no absorption. So to conclude, we have 2 effects: location of the source, dimensions of the object, and type of gamma emitter that we are using. They all contribute in a different way to the attenuation of the X-ray in emission computed tomography. So what are the basic steps in correcting for this distortion in image intensity due to attenuation? What are the basic steps in attenuation correction that we can do? So here we have the image again. This is what we've measured in our sphere of a homogeneous signal. We will calculate the linear attenuation coefficient as a function of position, and we can use that for attenuation correction. So we use this is the measured, with the measured linear attenuation coefficient, or calculated, and we can correct the image intensity. So that is the basic principle of how attenuation correction can, in theory, be corrected. So how is this procedure, proceed? We'll take an estimated object geometry and an estimated linear attenuation coefficient, or even a measured linear attenuation coefficient. We'll calculate the transmission loss. This transmission loss is a function of the projection. Where are we? How are we? Which projection orientation are we measuring? And so it's a function of the distribution of the linear attenuation coefficient over the object, but it's also a function of the specific projection that we are registering. So here's our object. We have the measured intensity here, and then we can calculate from the transmission loss. Here's the transmission loss characterized. We have the true activity. This gives us the transmission loss. We can calculate a parameter A as a function of position X and Y. It's 1 over the transmission loss. That's the attenuation correction. This would look in this example here like this. So we have to do more correction at the center and less correction at the edges. And then we will calculate a corrected activity profile or image by multiplying these 2 terms, the measured activity C with the correction parameter A. And this would then we get the image here. So this corresponds to this image, or this corresponds to the correction calculated based on this, and this here corresponds to a cut through this, which is corrected. So that is in principle the attenuation correction procedure that one could apply. However, there is a problem, a practical problem here, and that is we need to know the distribution of the linear attenuation coefficient in our subject, in our organs. We also need to know where is the source of the X-ray that we detect, and both of the things are not perfectly achievable. While we can, with, for example, computed tomography, get an estimate of the correction matrix. This is the correction matrix of the thorax. We see the heart here, we have the lungs, here's the spine, rib cage on the outside. We could in theory calculate that, but if we do detect the X-ray in our scanner, we don't know where it came from. We detect an X-ray here. Did it come from here? Did it come from here? Or did it come from here? On average, we don't know. So it's difficult to apply in practice this attenuation correction. And actually, believe it or not, because of that, the attenuation correction is rarely applied, and only in special circumstances because of these complexities. Now, I want to discuss one way of how one can simplify the attenuation correction. It is not a generally applicable procedure, but it's a nice introduction to attenuation correction that we'll discuss for the next imaging modality next week, and that is positron emission tomography. The problem that we have is that the correction is spatially dependent, it's source dependent. So now we'll consider a point source here at this particular point in the subject's head. It's tissue radioactivity CT at position XY, that's the tissue radioactivity. And now what we will do, the solution to simplify this is to consider the geometric mean of signals that are acquired at 180 degrees opposite. So I'll first introduce the position of our object. We have the distance from our object to the left end of the subject is x1, and distance from our object to the right end of the patient is x2. So the dimensions along x of our object at this point is given by x1 plus x2, and we'll call that big D. So now we have the signal S1 that's detected on the left side. We'll consider perfect collimation here, and we have a signal S2 collected on the right side from this point source. So I'll give you the explicit expression here. We have the tissue radioactivity x1y, so that's position x1 y seen from the detector 1, times e to the minus mu x1. We'll assume here for simplicity a homogeneous linear attenuation coefficient. On the right side, we have the signal S2 is given by the same tissue radioactivity times e to the minus mu x2. These are really not equal signs, they're proportionality, but we'll just, for simplicity, we'll forget all the proportionality constants here. So now what can we do? We'll take signal S1 and S2, multiply them by each other, and take the square root. That's what we've done here. So we'll take the expression on the left, this one, multiplied by the expression on the right, this one, and take the square root of that. The CT, the tissue radioactivity, we can take that out of the root because that is in there squared. Then we have e to the minus mu x1 plus x2. And that is equals to the square root of e to the minus mu d. Reminder here, d is equals x1 plus x2. So if we now simplify that, then we have the geometric mean, that is the multiplication of S1 with S2, taking the square root, that's equal to the tissue radioactivity times e to the minus mu d divided by 2. So this now means that if we collect our signal this way from our subject, we no longer have to be concerned from where exactly the X-ray in the body is emitted, but we only have to consider with the total travel distance of the X-ray through the object along the left and the right, the total travel distance passing through the object. This correction works in this example for a pointwise source. It works in reality if the uptake is limited to a specific region, so focal uptake, not over, if the uptake is diffuse over the entire body, it will not work as nicely as if we're looking at a focal uptake. And one example here are the heart scans with emission computed tomography, where the heart has an intense uptake and the rest of the body surrounding the heart does not have such an intense uptake. To summarize, we measure at 180 degrees opposite the signal S1, S2, simultaneously, multiply them, and basically take the geometric mean. And then this means that the attenuation correction now we have to apply to the signal for each radon, for each projection, depends only on the dimension of the object along the measured radon transform, that is, if you will, the thickness of the object, d in this case. So this is a simplification, but clearly if we do a scan in this direction, we have the scanner here, or if we have the scanner here, the distance that the X-rays in total pass through is different for this dimension and this dimension, at least for most of us.